Hello everyone. So in the previous lecture we discussed about in the previous lecture we discussed about classical and quantum indistinguishability or quantum okay, and we found there are broadly two types of two types of quantum systems, or two types broadly. Bosonic and fermionic. So also, I mean, there was another one which we will not discuss in the class, which is anyons. Okay, so let's for the moment stick to so for the moment we will discuss bosonic particles. So let's say there are n bosonic particles, and then in one of them, so first for simplicity let's discuss that all of them are in different states. Then the wave function is okay. So in this case the wave function is this, and because of normalization I put 1 over n factorial in the square root of 1 over n factorial. Whereas if this particle, if some of these particles, so this is the case, when all of them are in different states. So let's discuss if some of them are in same state. Okay, so in this case, let's start from again a very simple example. Let's first discuss two bosons are in same state. So in this case, the wave function is simply, for fermion this case is just 0, but for boson this case is simply this, because you see the wave function is explicitly permutation symmetric. So the wave function is simply the product of two wave functions. Okay. So now let's discuss the case when n particles such that n1 is in state I1 and dot dot dot. So this sum is basically the total number of particles, but it's in such a way that some of these particles are in same states. Okay. So in this case, the wave function is where P is distinct permutation. What do I mean by that? So in this case, for example, let's go back to this case. In this case, exchanging 1 and 2 just doesn't give any different result, doesn't give any different wave function. So that means this exchanging 1 and 2 is not part of distinct wave function. Whereas, if there was other case, in this case of the previous case, where if the two particles are in different states, then if I exchange those particles, then distinct permutation means that it gives rise to a different wave function. Okay, so here P stands for distinct permutations, and you can easily convince yourself the number of distinct permutations. So this is basically, okay, so there is a square root here, and in this case the number of distinct permutation is okay, so this is the number of distinct permutation, and hence the square root of inverse of this factor actually appears in the normalization. Okay, so this is the wave function for n bosons, where some of these bosons are in same state. Okay, now you notice, so this is one is a product basis. To discuss about in free bosonic system. Now, because this system, these particles are all identical and indistinguishable, so rather than to talk about which particle is in which state, there can be another basis where we refer to a state of the multiparticle Hilbert space simply by the occupation number in a particular state. Okay, so for example, the above case, we just denote it in this way, that there is a n1 state and there is n2 states and then dot dot dot. Okay, so this is same as the above wave function. So in the above wave function, we tried to construct the wave function by taking product of individual wave functions, and in this case we have to explicitly sum over distinct permutations. But question is that if we cannot, so in this case we sum over, in this basis we sum over distinct permutations. But point is that since we cannot anyway distinguish them, what's the point of at all labeling them and then doing the sum over distinct permutation? Rather, we just don't care which way, whether particle 1 is at state 1 or particle 2 is at state 2. Rather than that, we just characterize states of the multiparticle Hilbert space by saying, simply by saying that what is the occupation number of a particular label. Okay, so in order to understand this, let's just consider n harmonic oscillator. Okay, so in this case of single particle harmonic oscillator, we know the energy levels. So there is this half h bar omega, then 3 by 2, then 5 by 2, 7 by 2, 9 by 2. So these are this gap is h bar omega. Okay, and let's discuss the case. Just let's talk about the case where, let's say there is no particle in the ground state, one particle in the first excited state, two particle in the second excited state, no particle in the third excited state, and then one particle in the four excited states. Okay, so this is the case. So in this case the total number of particle is 4. So then in the occupation number basis, we can just denote this state as 0 particle in the first state, which is the ground state, then 1 particle in the first state, 2 particle in the second state, 0 particle in the third state, 1 particle in the fourth state, and of course 0, 4. Okay, so this is the representation in the occupation number basis. The advantage of this basis is that the bosonic statistics is inbuilt into it. The statistics is inbuilt because here we never talk about to begin with, we never talk about even distinguishing the particle. We never talk about, because we never refer to label of the particle. Okay, so that's the advantage. Okay, now if this is the advantage, if statistics is inbuilt into it, a very natural question is how to represent operators. Okay, so in order to discuss about that possibility, let's rather than going into the most general discussion, let's just discuss about again two cases of another simple example. Of two identical particles. Okay, and let's say there is a simple operator and also for simplicity, let's also say that it's only a two-state system. Okay, so typically bosonic systems are not finite dimensional, but just for simplicity, it's a two-state system, which means the Hilbert space of single particles are two-dimensional. Now consider a very simple operator, one particle operator, which is of this form. Okay, which means it takes state I and map it into state J. Okay, so if this is the case, then let's consider a very simple case. Let's first discuss the case when Ni equal to 1, Nj equal to 1. In this case, the state in terms of the product representation is this thing, just the two permutations, and let's also discuss the case Ni equal to 0, Nj equal to 2. In this case, this is just J1 and J2. Okay, now you can see that if I now construct this operator P of the multi-particle states, so let me denote it as script let me denote it as P underscore, which is same as P1. So this is the single particle operator, okay, underscore and tilde. So this is same as P1 J this and P2 Ji. Then we can check explicitly that P, this multi-particle operator acting on Ni equal to 1, Nj equal to 1, simply gives square root 2 times Ni equal to 0, Nj equal to 2. This implies there is a non-zero matrix elements of the operator. Okay, so this is the non-zero matrix element of the operator, and this square root 2 factor is often called Bose enhancement factor. The reason behind this factor is basically because we are summing over all distinct permutation, and that's why this enhancement factor happens, Bose enhancement factor. Okay, so this is a very simple minded exercise, but we can easily generalize it to n particles. Okay, so we will consider this generalization, and when we will do this generalization, we will see, first we will do this generalization, and then we will try to discuss about how to represent. After that, we will do how to represent operators in the occupation number basis. Okay, so we will consider it in the next lecture. I also encourage you to think about this problem, that how, rather than doing this computation, how can you generalize it? Okay, so we will do that in the next lecture, but also we end with one interesting thought. So we consider up to this point the number of particles to be some fixed number, one identical one particle state, two particle state, three particle state. But in the occupation number basis, there is an interesting state where the occupation of every level is 0. So in the occupation number basis. So at this point I am not keeping, so in this discussion, let's relax the number. So then in this case, occupation number, there is an interesting state where the occupation is 0. Okay. Okay. Note that it has no analog in product representation. Okay, and this plays a very important role later when we'll see in the discussions of quantum field theory. This is often called the vacuum state or the null state, not the null state, sorry, vacuum state. And it will play a very important role later when we will analyze the thing. Okay, so in this lecture basically what we discussed is that we discussed two different bases to deal with fermion, to deal with boson. One basis we already knew, it's the product basis, which we constructed out of product of single particle Hilbert space. And second is the occupation number basis. And then in the occupation number basis, we analyzed the case of a very simple operator and its expectation value between two states in the occupation number basis. So analyzed the matrix element of a simple operator in the occupation number basis. Analyze the matrix element of simple operator between two states in the occupation number basis. Okay, so in the next lecture we will see how to generalize this and how to define these operators in the occupation number basis without referring to the product basis. Okay, so that will be the discussion for the future next lecture, and we end here. And we encourage you to think about this question, that how to generalize this, so that you already have some idea before the next lecture.